In this lecture, we start with a formal definition of the circular convolution of two sequences. So given two sequences which we are going to assume are finite duration or finite length, let's call those sequences Gn and Hn. So if we are given these two sequences, the circular convolution between them is defined as an n-point circular convolution. So there is always some number associated with circular convolution. Let's define the output to be Ycn. So we call Ycn is given by circular convolution of Gn and Hn, and this is given by summation for m equals 0 to n minus 1. We have to be clear here that n is always in circular convolution, at least for the purposes of this class, we are going to assume is greater than or equal to the length of both the finite duration sequences. So we have n greater than or equal to max length of Hn and length of Gn. So if we make that assumption, then circular convolution is given by this summation m equal to 0 to n minus 1, and then we can pick any sequence. It is commutative, similar to the case of linear convolution. We do h of m, and then we have g of n minus m, which is very similar to linear convolution, but we have the circular convolution involves n minus m mod n. So we do that, and that completes the definition of circular convolution. Now let's look at its differences with linear convolution. Similar to linear convolution, what we have is we have this summation and we fix one sequence. In this case we are fixing hm, whereas the other sequence, instead of linear flip and linear shift, we have that we circularly flip the other sequence, Gn in this case, and then we circularly shift that sequence by an amount n to get Ycn. To reiterate, linear convolution of two finite duration sequences will have a similar expression, but what the difference will be is that instead of the circular flip, we will have linear flip. So linear flip in linear convolution is defined as g of minus m. In the case of circular convolution, we have first a circular flip of the sequence Gn. So circular flip is defined as g of minus m mod n, and we can interpret that more carefully by looking at the case of m equal to 0 and m not equal to 0. So g of minus 0 mod n is simply g of 0. So circular flip keeps the g0 entry at its original location, but g of minus m mod n, when m is not equal to 0, is given by a simple relationship. G of minus m mod n is equal to g of n minus m. That is for the case of m not equal to 0. Now this is the mathematical definition. We can also have a graphical representation of this circular flip by having this circle and then labeling on this circle the indices. So the indices start from n equal to 0, then we go to n equal to 1, n equal to 2, and we keep on going till we reach n equal to n minus 1. Let's also label n equal to n minus 2. So for the original sequence Gn, we have at index 0 G0, G1 at index 1, G2, G of n minus 2, and G of n minus 1. So this is what we start with, the original sequence Gn. Now, once we have Gn, we are interested in the circular flipped version of this Gn, which is given by G minus m mod n. So if you look at this graphical representation, what that means is that we fix the G0 at the index n equal to 0. But once we go to index 1, we should actually start reading the values from the index n minus 1 and start going in a counterclockwise direction. So Gn minus 1 in reality will be now at index n equal to 1. Similarly, at n equal to 2, we will have Gn minus 2 and so forth. So what we can do is now make a new circle and put indices on that, n equal to 0, n equal to 1, and so forth. This circle, what it is going to do for us will be representing the circularly flipped sequence. So how do we now fill in values in this circularly flipped sequence? Well, at n equal to 0, we have g of 0. We said that is fixed. But when we go to n equal to 1, what we do is actually start reading values of Gn from the index n minus 1. So we have g of n minus 1 coming in at index n equal to 1. And we keep on reading the values in the counterclockwise direction and start putting them in a clockwise direction in our new circle. So we get this new sequence where at n equal to 0 we have G0, but after that we get Gn minus 1 at n equal to 1, then Gn minus 2, Gn minus 3, and we keep on going with this till we reach G1. So to get the final sequence, all we have to do is flatten this circle into our usual straight line. So we get g of minus m mod n as g of 0 at n equal to 0. Then we simply go to the case of n equal to 1, where we get g of n minus 1. As we can see from the circle, we keep on going, we go to n equal to n minus 1, we get g of 1. So we can now go back to our definition of the circular convolution, which is YCN equals summation of HM m equal to 0 to n minus 1 g of n minus m mod n. Now notice that this n minus m mod n can be written as minus m minus n mod n. So what that mathematically means is that if you are interested in computing the nth sample of the circular convolution, then we simply circularly shift the circularly flipped version g of minus m mod n by amount n. So for every circular shift of the circularly flipped sequence g of minus m mod n, we shift it by n, circular shift, and then we multiply that sequence with hm. We add all the quantities from m equal to 0 to n minus 1. And if we do that, then we get back our sequence YCN. So for YC0, for example, all we have to do is multiply HM with g of minus m mod n. We don't have to shift it. So for YC0, we just multiply this sequence that is right there on the screen with the sequence H0. We multiply the respective entities and we add them all up. So a figure for YC0 would look like the following. We again draw a circle, put the indices n equal to 0, n equal to 1, n equal to 2, and we keep on going. We go up to n equals n minus 2 and n equals n minus 1. Actually, I made an error. It should be all m, the indices, since we are doing summation with index m. This should be m, and in the previous circular diagram the indices should also be m for the circular flip, because I'm writing it as a function of little m. So these are all m. Now going back to the original circle, what we have is at m equals to 0, we are multiplying h0 with g of minus 0 mod n, so that is g of 0. We are multiplying that with h of m, so we get g of minus m mod n being multiplied with h of m. So at m equal to 0 we get h of 0 and g of 0. At m equal to 1 we get h of 1, but now g of n minus 1, due to the fact that the first sample of my circularly flipped version is g of n minus 1. At m equal to 2 I get h2 g of n minus 2. Similarly, m equal to n minus 2 I get h of n minus 2 g2. m equal to n minus 1 I get h of n minus 1 g1. Now to compute my YC0, I just multiply these quantities. So g0 h0, I multiply all the other ones, h1 g of n minus 1, and then I add up all of these quantities to get the required 0th sample of my circular convolution. So YC0 is simply add all the multiplication factors in this circular diagram that you see. Now this is for YC0. If we want to do YC1, for example, the formula says that we basically now just shift the circularly flipped version by 1 to the clockwise direction, and we simply multiply that with HM sequence. Now the question to ask is, what happens if H and G don't have length equal to n? Then we do what is called zero padding. If they don't have the length n, they are smaller than that, then we simply make all the rest of the entries up to n minus 1 as 0. And then we can carry out these operations. So as an example, if h1 was equal to delta of n, technically this is a length 1 sequence. At n equal to 0 we have 1, but we can now add 3 more zeros to make it a length 4 sequence. Now let's talk about the case where we are interested in calculating YC1. Let's write the formula, that is summation m from 0 to n minus 1 h of m g of 1 minus m mod n. And again we'll write it in the fashion where it is clear what is the relationship of YC1 to the circularly flipped version. So let's write that down. Summation hm g of minus m minus 1 mod n. What this means is that we are now multiplying our sequence hm with a circularly shifted by 1 sequence of the circularly flipped copy. So circularly shifting g of minus m mod n by 1, that is the sequence that we will multiply with hm. Now since we understand the relationship of YC1 to the circularly flipped version, we can again go back to the circular diagram that we have been using. So we simply label that diagram with the indices m equal to 0, and then we go to m equals 1, m equals 2, and we keep on going till we reach m equals to n minus 2 and m equals to n minus 1. Now when we look at the formula above, what we see is that the formula involves hm as it is, so we just simply put down h0 at m equal to 0, h1 at m equals 1, h2, then h of n minus 2 at m equals to n minus 2, h of n minus 1 at m equal to n minus 1. But now what do we multiply with h0? Well, that is the circularly shifted version of circularly flipped copy by 1. So we go back to our sequence, which is the g of minus m mod n, and we simply move all the sequence values of g to the clockwise direction. So whatever g value was at m equal to n minus 1, that will be now used at m equal to 0. What was at m equal to 0 will be used at m equal to 1, and so forth. So at m equal to 0, we get, instead of g0, now we get g of 1, because g of 1 was previously at n minus 1. Now going forward, at m equal to 1, we will get a value of g which was at m equal to 0 previously. So if we go to m equal to 0, we see we had g of 0, so we now multiply g of 0 with h1. Similarly, we now get g of n minus 1 at m equal to 2, because that is what was previously at m equal to 1. And if we follow this strategy, at m equal to n minus 2, we should get g of 3. Similarly, at the m equal to n minus 1, we should get g of 2, because g of 2 was previously at m equal to n minus 2. So this means for yc1, we now multiply all of these quantities together, and then we finally add them all up. So yc1 is simply multiply and add all the quantities in our new circular diagram. Now we can move forward to yc2 by using a similar circular diagram, labeling the indices m equal to 0, 1, 2 up to n minus 2 and then n minus 1. Now we know that h will be put as it is, so we put h0, h1, h2, h of n minus 2 and h of n minus 1 at their usual locations. For yc of 2, we know that we need to now circularly shift by 2 the circular flipped version, or equivalently we have to shift the g sequence one more to clockwise direction from where it was for yc1. So whatever was for yc1 at m equal to 0 goes to m equal to 1, and whatever was at m equal to n minus 1 goes to m equal to 0. We had at m equal to n minus 1 g of 2, so that goes to m equal to 0 in yc2. Similarly, we get g of 1 at m equal to 1, and similarly g of 0 at m equal to 2, and this keeps on going. At m equal to n minus 1, we get g of 3 because that was previously at m equal to n minus 2, and similarly we get g of 4 at m equal to n minus 2. Now for calculating yc of 2, we simply multiply these numbers in this circular diagram and we add them all up. So we do the same process of multiply and add for calculating yc2. And we can repeat this process by simply going back again and again to our original circularly flipped version of the sequence g of minus m mod n, and simply rotating that original sequence for g clockwise every one by amount 1 for every next sequence value for ycn. and you keep on going till you reach n equal to n minus 1. So circular convolution is only defined for n equal to 0 up to n equal to capital N minus 1, and we repeat this process again and again till we are done with all the sequences. This approach to calculating the circular convolution is called graphical representation of circular convolution. You can use the formula directly also, but this is one way. Another easier way of computing circular convolution is what is known as tabular representation, which many people may find easier, and that is very similar to the tabular representation that you saw earlier for the case of linear convolution. So if we say that we have n equal to capital 5, I'll give you an example in that case how to use tabular representation for computing circular convolution. So our output sequence is going to be of length 5 for n equal to 0, 1, 2, 3 and up to 4, where this 4 corresponds to my n minus 1. So I start off with drawing 5 columns, one for each value of little n, and each one of these columns will be used to calculate my YC. So the first column will help me calculate YC0, the second column will help me calculate YC1, and so forth. I have a typographical error here. It should be n instead of little n in the upper row. Now in the rows, I'm going to put down the values of little m. Each row will correspond to one value of little m. Okay. So the first row is going to correspond to little m equal to 0, and that will have the value h0 first, h1 in the next row. So this is little m equal to 0 first row, m equal to 1 second row, m equal to 2 third row, m equal to 3, m equal to 4, and I will have h0, h1, h2, h3 and h4 in the first column. Now since I am keeping my h sequence as fixed, I will repeat that in each of the columns corresponding to the 5 output values. So I'll have it the same for n equal to 1, I'll do the same for n equal to 2, and I'll do the same for n equal to 3 and n equal to 4. If we had used G as a fixed sequence, then I would do this for G instead of H, but right now what we are doing is we are fixing H and we are going to circularly flip and circularly shift G. So now we have just put down all the values of H in the 5 columns. Now we start filling in what should go with each value of H in each column. So the first column corresponds to just the circularly flipped version of G, or G of minus m mod 5. So recall that when we do minus m mod n, we get for m equal to 0, we get G0. So the formula is G of minus m mod n, where n is 5 in this case, is simply G of 0 for m equal to 0 and G of n minus m for m not equal to 0. So the first column simply corresponds to this circularly flipped version. I just write down G0, then the next sample of my circularly flipped version, which is G of 5 minus 1 equals 4. So I get G of 4 in this next column, next row. Then I have G of 3, which is 5 minus 2. Then I get 5 minus 3, G of 2, and 5 minus 1, G of 1. So that completes my n equal to 0 calculation column, and YC0 is now simply given by I multiply all of these terms and then add them all up. When I do that, I simply get my YC0. Now for YC1, I'm keeping my H sequence fixed, but now we have to circularly shift this sequence, which is g of minus m mod n, by 1. So what does that mean? I basically push down all of the entries of this sequence down. So G0 now moves to the second row, G4 moves to the third row. So it goes down one row, G3 moves down one row, come to G3, G2 moves down one row, come to m equal to 4, and then G1 has no place to go. So what do? We put it back at the top for m equal to 0. So G1, which was previously at m equal to 4 or m equal to n minus 1, it goes back to m equal to 0, and that completes our circular flip. So we have g of 1 in the first row. Now this completes my second column, and I can now simply multiply and add all of these terms to get my YC1. We can now move on to the n equal to 2 index, and once again we do the same thing. We move down all entries by one row. So G1 moves to the second row, G0 moves to the third row, then I have G4, then I get G3, and since G2 has no place to go downward, it goes back to m equal to 0. So G2 now instead goes up. And again, I multiply all of these terms in each row. I add up all the quantities, and that will help me calculate YC of 2. So I can now go to the question of YC of 3 and do the same to the G sequence in the n equal to 2 column. Everything gets pushed down, and the last G3 goes back up at m equal to 0. And finally, I do the same for n equal to 4. I get G3, G2, G1, and G of 0, and G4 now again goes back to m equal to 4. I add all of these terms, multiply and add them in each column to get YC2, YC3, and YC of 4. So effectively, this tabular method helps you look at the circular shifting of the circular flipped version, and if you look at this figure, what you will see is that the main diagonal and all the other diagonals are actually constant. They have the same value. G0 in the first row, in the second column it's in the second row, and so forth. Similarly, you look at G4, G3, G2, so your off diagonals and main diagonals, they are constant, they have the same value. Okay. This structure, it's called a toplet structure. You can represent this operation in a matrix vector multiplication form, but we would not formally have that discussion in our class. It's just a way for you to see whether the tabular method that you have done, does it look correct or not. You must have constant, the same value of G if you go in the diagonal and anti-diagonal shape of this tabular method. One question that someone could ask is, what would have happened if we had actually gone for n equal to, for example, 5? Well, you could see that in that case you would have to now shift the G sequence in the last column for n equal to 4 column. And if you were to do that, you would see that actually you get back the same value, the same formation of the column as you got for n equal to 0. So this actually shows that circular convolution, if you are to calculate it for values n equal to 0 to n minus 1, if you go above that, it's actually periodic. Now let's move on to the circular convolution theorem in a formal manner. So what you are given is Gn and Hn, and if you circularly convolve them, the question is, what is the DFT of this circular convolution? Now before that, let's ask ourselves what are these values of n we need to care about. So the first assumption is that n is bigger than or equal to the length of my sequence Gn. Number two, n is bigger than or equal to the length of my sequence Hn. And once we verify that, where n is now the length of my circular convolution, we are doing n-point circular convolution. Once we do that, then we know that we are going to get a sequence which is going to be length n. Okay. So now we are asking what DFT to compute. So we are specifically talking about now an n-point DFT. Okay. So all the DFTs that we have in this formulation are n-point DFTs. So the circular convolution theorem says that circular convolution in time is equal to multiplication of the n-point DFTs of my sequence G and my sequence H. Now both are length n DFT of their respective sequences. So on the left hand side in the time domain you have a length n sequence, and on the right hand side you have a length n sequence in frequency. This is a very important theorem in the field of signal processing, and it actually has applications in a number of areas, including mobile communications, where something called orthogonal frequency division multiplexing relies on this theorem. So why is it important? Let's try to understand the circular convolution in terms of computation. So this is the definition of circular convolution: m from 0 to n minus 1, h of m, g of m minus n minus m mod n, and we have this going on for n equal to 0, 1 up to n minus 1. So if you stare at this expression, what you see is that for each little n, we need capital N multiplications, and we need n minus 1 additions. So computing each sample of circular convolution requires n multiplications and n minus 1 additions. Now what this means is, since we have total of n entries in our circular convolution, the total cost in terms of computation for circular convolution is given by proportional to n squared, or what is known as order n squared complexity or computational complexity. So this is what happens if you were to use circular convolution using the formula directly. But what the circular convolution theorem tells us is that we can compute circular convolution using actually DFT and inverse DFT. Now why is that an interesting thing to do? The reason is because DFT, unlike circular convolution, can be computed using the fast Fourier transform or FFT algorithm. And what do we know about FFT algorithms? That they can be solved in order n log n computational steps. So this means that we can use FFT to actually compute our DFTs in order n log n computational steps, and therefore this means that we can use DFT to compute circular convolution, and the complexity of the total circular convolution will be in that case order n log n as opposed to order n squared. Now this is huge savings when you are trying to use capital N very large. N squared is much bigger than n log n. So what is the step that you will take for computing circular convolution? You are given Gn, you compute its n-point DFT to get the sequence G of k. Then you have your sequence Hn, you use endpoint DFT to compute the sequence h of k. So now you have computed the DFTs of the two sequences and they are both endpoint. Now, according to the circular convolution theorem, you multiply the two to get gk and hk. And now if you compute the endpoint inverse DFT of this multiplied sequence gk-hk. So compute endpoint inverse DFT of gk-hk, then the circular convolution formula theorem guarantees us that we recover ycn, which is equal to gn circularly convolved with hn. And in order to compute this in a fast manner, what we really have to do is compute these endpoint DFTs and inverse DFT using the FFT and inverse FFT algorithm. Even though we are to compute one circular convolution, we are computing two endpoint DFTs and one endpoint inverse DFT. The total cost of that for large values of n is still much smaller because your computational complexity is scaling as order n log n. It is still much smaller than the case if you were to compute circular convolution directly, because that cost will be proportional to n squared. We now move on to the next theorem of the discrete Fourier transform, known as the modulation theorem. So just like in the case of the discrete time Fourier transform, we have the duality between multiplication in time and multiplication in frequency. We have a similar duality in discrete Fourier transform. In the previous theorem, we saw that circular convolution in time gives us multiplication in DFT domain. Now, modulation theorem says that when you multiply two sequences in time, both are length n sequences, and you take their endpoint DFT, then in the Fourier domain what you have is now circular convolution of their respective Fourier transforms with a scaling of 1 over n. The next property we want to study is the Parseval's theorem. Again, very similar to all kinds of Parseval's theorem we have seen before. What this theorem says is that if you compute the energy of a sequence, a finite length sequence in time, which is given by summation n from 0 to n minus 1 gn absolute value squared, then that is equal to the energy in your frequency domain or in your DFT domain scaled by 1 over n. So you have 1 over n summation k equal to 0 to n minus 1 gk norm squared. So Parseval's theorem in words can be said as energy in time is proportional to the energy in the DFT coefficients of your signal. And the constant of proportionality in our case is 1 over n because of the way the discrete Fourier transform was defined in our class. Okay, so this completes our discussion of the main theorems that we wanted to cover for discrete Fourier transform. Now let's go back to the question that we had raised a few lectures ago, which was that DFT can be used for both spectral analysis of signals, which we covered some time ago, and for processing of signals through linear time invariant systems. And why do we want to do that? The reason is because if we use DFT for processing of LTI systems, then that can lead to much faster computation as opposed to using the linear convolution formula directly. So that is what we are going to discuss next, which is that how to use DFT for processing of signals in LTI systems. So let's start with the problem we are interested in. We are given a sequence Gn and it is to be processed by an LTI system with impulse response Hn. The output Yn is simply Gn linearly convolved with Hn. Now we are interested in actually solving this linear convolution using the discrete Fourier transform formula. And the reason we want to do that is because of computational reasons. So if we were to use linear convolution formula directly and assuming that G and H both had, let's say, length n, then it turns out the complexity of that procedure is also proportional to n squared, which can be rather large. So what we want to do instead is use perhaps DFT in conjunction with the FFT algorithm to speed up the computations. But our challenge is that DFT, we only know the relationship to circular convolution and not linear convolution. So the question is, how is circular convolution related to linear convolution? And the answer is that actually circular convolution can be at times equal to the linear convolution. Now the big emphasis here is on can be. It will not always be equal to the linear convolution, but it can be made equal to the linear convolution. And the question arises, when does that happen? So to answer that question, we have to remember there is only one parameter in circular convolution, and that is the number of points of circular convolution. So circular convolution can be equal to the linear convolution depending upon the choice of the number of points, the choice of n that we use for circular convolution. So how should n be picked? For that, let's try to think about what is actually the length of linear convolution. So suppose Gn has length L and assume that Hn has length m. So the question is, if I convolve these two sequences of length L and m respectively, what is the length of my output sequence Yn? Okay, that is something that we have seen many times before. The length of Yn is simply equal to L plus m minus 1. Length of one sequence plus the length of other sequence minus 1. Now let's go back to the definition of the circular convolution. So define circular convolution YCN as an n-point circular convolution between Gn and Hn. Now remember that in this setting we need that n is greater than or equal to L and n also has to be greater than or equal to m. But in general, if we just satisfy this condition, then we are not going to get Ycn equal to Yn because Ycn is of length n. So circular convolution is of length n and my linear convolution is of length L plus m minus 1. So just satisfying the condition n greater than or equal to L and n greater than or equal to m is not going to make them equal. We are not going to do a formal proof, but it can be easily seen that if we were to actually make n greater than or equal to L plus m minus 1. So if n is chosen to be satisfy this condition L plus m minus 1, in that case what happens is that the circular convolution formula gives you an output which is the same as the linear convolution formula. Okay, so the thing to remember is circular convolution is not equal to linear convolution, but if the number of points of circular convolution exceed the length of your linear convolution, then Ycn circular convolution equals Yn. So now we know the relationship between circular convolution and linear convolution, and we know how circular convolution can be computed in a fast fashion using the DFT. So if we combine these two facts, we can argue that actually DFT can be used to carry out linear convolution in a much faster fashion than using the linear convolution formula directly. So we can now finish the main message of today's lecture, which is that we can use the circular convolution theorem and the fact that the circular convolution YCN equals Yn, the linear convolution, for n greater than or equal to L plus m minus 1, which is the length of the linear convolution, to compute linear convolution via the DFT. So we'll combine the lessons of this discussion and earlier theorems as follows. We are given a system Hn which has length m. It is input a signal Gn of length L. We are interested in computing the output Yn. So instead of using convolution formula, first we'll pick up a number n greater than or equal to L plus m minus 1. Now why is it not exactly equal to L plus m minus 1? Because of the fact that we want to compute DFT in a faster fashion using FFT. Now many FFT algorithms perform the fastest when the n that is selected is a power of 2, which means that we require n to be 2 to the nu, where nu is some integer. Okay. So that is why you don't always want to pick n equals L plus m minus 1. So if, for example, we were given that L plus m minus 1 is 101, then instead of picking n to be 101, it is better to pick an integer which is a power of 2 and bigger than 101. So the number we'll pick in that case is n equal to 2 to the 7, which is 128. So that is why you should always keep the condition n greater than or equal to L plus m minus 1 in mind, and remember that you will perform the fastest when you pick n to be a power of 2, which is the restriction that comes up from the FFT algorithms. So once that is done, we simply apply now our DFT and circular convolution relationship. We get Gn. We compute its endpoint DFT, where n satisfies the condition. Using FFT, we do the computation. And then we do the same for our system Hn, system impulse response. We also compute its endpoint DFT using FFT. Then we simply multiply the outputs of these FFTs, which are GK and HK, and whatever comes out, the multiplication factor, we simply compute an endpoint inverse DFT via the inverse fast Fourier transform algorithm. And if we do that, then we get the circular convolution YCN, but by the argument that n is greater than or equal to L plus m minus 1, we are guaranteed that YCN is in fact equal to Yn, which is just Gn linearly convolved with Hn. So this is the procedure by which you can carry out linear convolution using the DFT, and in fact using the FFT in a much faster fashion than if you were to use linear convolution formula directly, which has a much higher complexity. The only thing to keep in mind is you must ensure that the n that you use is bigger than or equal to L plus m minus 1, length of both the sequences. Now, one thing that you should keep in mind during this discussion is that this description assumes that you have the full sequence Gn or signal Gn available to you before you can do the processing. Now in real world, it is a rather difficult thing to ask that all the signal that you are going to process is already available to you. In addition, if we use this method for signals that are too long, then that will create a large delay before you can have your output ready. So in real world, for very large length input signals, actually what is done is that a long input signal is chopped up into small sized pieces, and as the new data comes in, it is collected up to that small size, and then it is processed through the LTI system using this procedure. Now, when we do this chopping up of the signal, we have to be careful how do we align back the outputs of these chopped up pieces. So that is a really involved topic that we are not going to discuss in this class, but it is important for you to keep in mind this aspect that for signals that are either too long or for signals that you need to process in real time, you do not apply this procedure as it is, but rather you go through the process of chopping up of the signal. So to reiterate, the case when the input signal Gn, which is the input signal, is too long, then we do not process that input signal using the above procedure as it is. And the too long does not necessarily have to mean that you have acquired all the signal beforehand. It could also be the case that you are acquiring the signal in real time and you don't know what the length of the signal will be. So in both the cases, this block diagram should not be used in its exact form. A version of this block diagram still will come into play, and how it will come into play is that we will basically chop up our input signal into small pieces. We will process each of the pieces using this very block diagram. But the question then arises, how do we fit those two pieces together? And there are two main ways of doing that in the literature. Again, we are not going to cover those pieces, but it is important for you to be aware of both the procedures. There are two ways. They differ in the way you basically patch up these chopped pieces. So one of those ways or methods is called the overlap and add method. This is basically based upon how the pieces are aligned, how do you add them up. And the second method is called overlap and save method. This is a little different procedure than the overlap add method. Both the methods are there to help you process either signals in real time or signals that have been collected but they are too large in length and you want to produce the output right away. So keep that in mind if you are interested. The text has description of these two methods. You can read more about that, but we'll end our discussion at this point.